I'd like to welcome everybody. Thank you for coming today. This last session is tips and tricks on flow simulation. I've been talking all day, so my voice is getting a little bit hoarse. Can everybody hear me okay? Am I speaking? Turn the volume up. I'll try. There we go. I'll try to speak. Hopefully I'll get a little louder as we go. My voice, my vocal cords will start to strengthen up here. I always have difficulty with this because I know there's a lot of different people with a lot of different backgrounds in here trying to give you something for everybody. So I have a lot of different things. I try to start very generally and try to get into some more specific things, so hopefully everything I show will help somebody in some little way or not. So I'm going to try to do a little bit, open up the program, a little bit with the PowerPoint, maybe go back and forth between the two, depending on how much time we have, how many questions we have. We'll try, we can keep this informal if you have any questions while we're going on, because I know it's kind of hard after I've moved on to other things to ask later. So if you have any questions, I'll try to answer as best I can. If not, we'll take it later, or maybe even through email if it's very time consuming. Okay. Just to give you a little background on myself, I'm a technical support engineer with SolidWorks, and I exclusively support flow simulation. I've been doing that for about 10 years now. I've been using CFD since about 1994, and I was in the aerospace business 10 years before that, doing some project engineering work. So I've got a little bit of experience both on the project engineering side and on the analysis side. Okay, as I said, I'm going to start general. I always like to start this kind of light to tell you the latest that's going on in fluid dynamics, just some interesting things I've seen. I love fluid analysis. It gets me excited. It's what gets me to work every day. And these are a couple of things I just saw recently, and I thought I'd present it here today. For people who are not too familiar, some customer resources for finding out your information. And then we're going to go over some tips on using some new commands that are available, some new features in flow simulation, and then some general meshing tips, and if we have time at the end, maybe some electronic cooling tips for people who are interested in that. Okay. As far as customer resources, I know most people are probably familiar with the website because it's been several years now that it's been out, but I thought I'd still mention it. You can log in and to the site that's shown in blue over there. And what's really nice is there is a forum there for flow simulation. If you drill down, select simulation, and then under simulation is flow simulation. And you see people asking questions and other users helping out other users with their questions. There's also a knowledge base that we're constantly adding as time goes by. A lot of people have been adding stuff, and it's been growing over the years, and it's getting quite extensive. So you might be able to find out some of your questions that you have there. You can also keep track of any SRs, service requests, or SPRs, which are bug announcements and things like that from this site. You can make enhancement requests, which are always very important. We always love to hear from our actual customers, and you'll notice, and I'll try to point out a few things as we go on, that whenever I do these, that we're actually customer enhancements. A lot of things you see in flow simulation are customer enhancements. Over the last 13 years or so that flow simulation has been out, it's been improved because of people like you have put in stuff directly from this site also. And then there's a few other things with the renewal, and you can have your own profile on there also from that point. Now, that's specific for SolidWorks and flow simulation. A lot of times people ask me, where can I get information about CFD in general? And this seems to be a site not that I myself also use, but I know a lot of other CFD engineers that use that blue site, the cfd-online.com. They have a wiki on there that gives a lot of general descriptions about the Navier-Stokes equations, if you're interested in getting into the actual equations that are solved with flow simulation, which is a full computational fluid dynamics software package. They've got a nice jobs database, events calendars. They also have online discussions, resources. They have book guides on there, recommended books for CFD if you want to get deeper into that area. Okay. These are one of the things that I said I see throughout the year. And actually, this was pretty recent. This was in Aerospace America. If you belong to AIAA, which is Aeronautics and Astronautics, you'll get a copy of this magazine just for subscribing. But this is kind of the state of CFD. I do not know how familiar people are with computational fluid dynamics, but there are no closed form solutions for it, especially for the turbulence parts within there. And there's every university, major university in the world is working on trying to solve a closed form solution for these Navier-Stokes equations. And what you're seeing there is why it's so hard. This is turbulent flow near the wall. And you see those streaks, those kind of red streaks. They've been seeing that, and they've been studying that for a long time, and they've actually been able to simulate it in this was an Air Force Research Laboratory funded project by the University of California, Davis. And there's a nice article in there about how, and in some, if you're familiar with DNS, which is direct numerical simulation, which tries to solve the Navier-Stokes equations directly, they can sort of simulate this now, but it takes weeks on the fastest computers in the world to run it. I mean, it's nowhere near being able to run any type of applications that we see every day in the project engineering world on there. But they're getting there, but it's probably going to be another 10, 20 years, 30 years before we see any big stuff going on there. So what I showed you was some turbulence near the wall. What's interesting is a lot of the stuff that we see in small enclosed places also happens globally. If you look on the lower left-hand corner, there's actually an island. This was taken on October 18, 2012. And you can see that there's actually what they call vortex shedding coming off a very large volcano or mountain. And this is a satellite image that NASA took. And what's kind of cool is we actually can see this on little cylinders that maybe you have an electronics cooling problem, or if you do a time-dependent analysis, this is what's called unsteady flow. So it actually happens on the global scale because we actually live in the boundary layer on the Earth. As we're walking around, we're actually walking through a boundary layer, but unfortunately you can't really see it. But turbulence there. I heard that in Oklahoma, some places where it's really dry and on days where there's a lot of vapor clouds, you can actually see that previous slide that I showed you where you can see the streaking of the turbulence. It's a very rare atmospheric event, but it does happen once in a while. And here's one more image showing the von Karman vortex streak. This is another NASA image that was taken October 30th, just south of South Korea, I believe. There's a pretty large volcano there that caused some vortex shedding in the Earth. Okay, that's a little bit of fun on the fluid side there. Getting back to flow simulation here, what I'd like to show you is some more resources that would help you out here. There's 3 documents. The people who are probably longtime users of flow simulations probably familiar with this. But these are good, especially for beginner or intermediate users. And they're called Solving Engineering Problems, Technical Reference, and Tutorial, and they're in that website link that I have at the bottom. So if you have flow simulation installed on computers, you can find these. And there's very good validation examples, which I'm going to show you a little bit later, just to put some points together that I was trying to show. There's very nice step-by-step. And what was nice in 2013, they have another folder in there. The problems that they use for the tutorials, they're all in a similar directory, and they got ready to run. So before, they used to just put the tutorials without being set up. Now you can actually find a folder with the tutorial actually set up, so you don't have to walk through it. You can actually look at one that was already set up from big scratch. So it gives a nice big help. And then the Solving Engineering Problems has some nice sections on meshing, which I'm going to show a little bit today. They have some nice sections on rotating flow, humidity, steam, cavitation. We'll talk about a couple of those, not all of them today, but it's sometimes good to go in there and see if there's a problem that you're having. You can look it up and get some information. And I use it a lot of times just to get some familiarity with certain aspects of the flow. Okay, one of the new features in the flow simulation is the parametric study command. They've kind of reworked it, this feature. It works similar to the way it did before, except they've kind of redesigned it in a way that's easier, maybe more efficient for some people to use. And what they've done is they've actually broken it down into 2 buttons now, and they've actually moved the location. So people who have used it, they'll be familiar that it was in 2012 and earlier versions in the flow simulation drop-down menu under Tools. You would find parametric study. Now they've moved it into the flow simulation drop-down menu under Solve. You'll see Run, Batch Run, and then the parametric study command. Okay. Now, I'll show a few more slides about what each of these 2 options does. And I'll start going through it. But basically, the what if allows you to change the flow rates, dimension tables, and just do, it's kind of like cloning, except you can do it all within the parametric study command. Where the goal optimization is more, you set a goal and you have a target, and you monitor it, and it iterates on that goal to that target, or to the boundary condition until you get your target goal. Okay? So both the what if and the goal optimization, these are typically the features that are available for running the parametric study command in 2013. Those are the options that you have available in general settings: the roughness, the ambient conditions, the external wall, the input data list. They show you how to use the different boundary conditions that you have within the input. The ones that aren't used will not be listed, but velocity, mass flow rate, pressure, temperature are all available. Now in SolidWorks, you can actually set up a dimension within your SolidWorks feature manager tree and use it in the parametric study command. And so you can actually, if you have a valve and you have a certain opening for that valve, you can actually, and you want a certain pressure drop, you can either do a goal optimization matching a pressure drop or matching the particular opening of that valve to get that particular pressure drop. Okay, and you can also design tables. Okay, so again, the what if study is in the flow simulation solve parametric study command. So that's probably the most important thing right now, is to understand that they moved it from the tools to the solve command. And if you have a previously created parametric study, you can actually load it with with a file that you save, so you don't have to recreate the parametric study each time. And that file that's saved is a FWPS file. So once you create it here, then you can save that file, and then if you want to use it later, you can actually read it in and use the same dimensions that you did before. Okay, and this is kind of what it looks like on your screen here on the right, on the lower right-hand side. And what I'll do is I'll actually open up and show you an actual model file here. So if I go to the flow simulation drop-down menu and go to Solve, you can see there it is, Run, Batch Run, Parametric Study Command. And here is actually the input value. What I have is just a simple pipe flow, inlet, outlet. And I have, here's my boundary conditions, environmental pressure on one side, inlet mass flow on the other side. And we have a number of goals here set up, a global goal for maximum velocity, a surface goal for mass flow rate. And then we have these 3 goals. One is measures the inlet pressure, the outlet pressure, and then the pressure goal here is an equation goal that just subtracts the inlet and outlet pressures, okay? And because that's going to be what we're going to use as our output target parameter. So what I did was, in here, we have what if and goal optimization. So I selected what if, and I said mass flow rate, let's start at 0.01, and just run these mass flow rates, 0.01, 0.2, 0.3, 0.4, 0.5. And then I want to know what the pressure drop, the global goal maximum velocity, and the surface goals are. And then it runs it, and you can see it creates, in the configuration manager tree, it creates a configuration. So you can actually go, so it's like cloning the project without you having actually going to clone it. And it has a different mass flow rate for each one of those. So you can see how this could be a nice time saver because you just go out and set up and run this almost like the batch run command and just have it all solved. And these are the results that you get out of it. Design 0.1, 0.2. So this was the 0.01 flow rate, 0.2. And it tells me how the pressure drop changes for each of those flow rates. The global goal maximum velocity, the flow rate, that was the boundary condition. Okay? And they actually have some additional options here. You can mention how many cores you want to run it on, whether you want to save the monitor, and whether you want to save the project. So if you don't want to save all these projects, you could just unselect that. Okay? All right, so let's talk a little bit about the goal optimization. It's kind of similar to the way it works, except we got a little bit more setup to do here. Again, this is in the flow simulation solve parametric study command. It's that little button underneath the what if, and I got an example, I'll show that to you. And you select an input parameter to vary and specify values denoted by a certain variation range for your output. So on the outlet parameters, you select a goal of interest and specify these target goal values. And on the scenario tab, study options, you define your finish conditions, when to stop the runs for each one for the optimization. So it doesn't go on forever. You can say try 10. If you can't optimize it after 10, then you kind of look at the results and decide, do you have to change your range? Is there something about the model that it's never going to be optimized? So there's a number of questions that you have to look at the model to figure out why it may not have optimized on a particular output value. So again, you need goals, you need parameters, and what I just wanted to show on this slide over here is the optimization is actually using an iterative secant method. And so as it's tracking through, so it's kind of like the what if study, except it's actually trying to get to a certain specific point instead of just plotting out results for each iteration. So once the goal and your particular target value, once they meet, then you've reached your optimized point. Okay? You can specify an initial value if you happen to know that the solution is, or the target or the starting boundary condition is a certain value, then you can enter that and it'll actually get to the optimized finished case a lot faster with a lot less iterative processes in between, okay? Now, I mentioned earlier, if for some reason, let's say you do 10 loops through this where it's varying your particular flow rate or whatever you're varying, and you don't get to the solution, then you get 3 different types of messages. Solution converged, which is probably the best message. That means you actually found an optimized point. Solution is not found, maximum number of iterations. So in this case, you must likely increase the maximum iterations. So you may have to iterate some more. It needs a little bit more iterations to go through. Or the solution is not found, and maybe the variable range that you set is too small for that optimized point that you're trying to look for, okay? And again, it's just explaining in this next slide about the iterative secant math that calculates the next variable based on values at 2 previous iterations. So for the first approach, the specified min maximum variables are always used. So it looks at the min, it looks at the max, and it tries to find a value in between. It's assumed that both the parameter and the goal functions are monotonic, monotonically decreasing or monotonically increasing with that. And this just basically shows that the solution is not found if the x min of the goal is less than the x min is less than the parameter min, or the goal max is less than the parameter max, or vice versa. And both those graphs show basically the min and max. And you can see there is no intersection point, so it didn't find the optimized point. So that's where you would see a solution is not found for this particular case. And just like the what-if study that I showed you, it has a very similar look to it in the parametric study as far as results. And I have a simple model here to show you on that. Let's see now. Okay, if I go to the flow simulation solve parametric study command again. All right, so this time, this is the goal optimization was selected in this option here. And you have your mass flow rate of 0.01. Okay, and we're varying this flow rate from 0.01 to 0.09. So the iterative secant's first going to try 0.01, then it's going to try 0.09, and then it's going to go in between. My output parameter is my pressure drop. My target value is I want to get a 0.9 pascals. This is a very simple pipe, so there's very low pressure drop going on within here. And then if we go to the scenario, you can see that it went through 5 iterative steps, okay? And you can see how it calculated different pressure drops, and it got closer and closer. By the way, you also put in the maximum deviation. I can show that to you over here. And you could specify a maximum deviation for the model is 0.05. So this so you want the solution to be within 0.05, and that's what we have for this particular one. And so I got a solution converged, and it tells you it's finished in each case. And so this is where you have to look at the solution. If you run it 10 iterations, then you have to figure out why the solution was not found if it wasn't particularly found. Yeah, there's a export to Excel button on there, and you can actually export your stuff to Excel. Okay, that's the parametric study, new feature. Another new feature is the comparison tool. And this is kind of nice for comparing a lot of configurations that you have within your project if you make a lot of different runs. So users can compare the results of various projects coming from configurations within the same model. Users can create summary tables, charts, and save active screen images. So it provides a better access for your results and enable designers to leverage all their results. So it's just, instead of having to go to each configuration and load results and show the cut plot, you can all do this from one configuration and do a comparison within each one. So let me, again, this is in the flow simulation results. So if you go to the flow simulation drop-down menu, it's under results and compare. You select the compare, or you can right-click on results in the feature manager tree. Okay. Let me just show you a quick demonstration of that. So you Okay, so now one of the things that you might notice with in flow simulation is the results. It'll tell you if your analysis loaded or not. So you can see right here it says not loaded in this particular area, or if there's nothing there, then it's loaded. Or if you just ran a mesh study without solving it, it'll say mesh only. So you'll know that you ran the mesh. In flow simulation, you can just run the mesh without solving it. And if that's all it finds, then it will say that it's just, before you would never know, you would have to load it first and then take a look at it. Okay, so I can right-click here and select the compare model. I ran this earlier. Let's see, let me, before I do that, so that you can see it, the active screen image, if I can get that, let me make it transparent. So I'm in this test case and looking at a velocity cut plot here. So if I go right mouse click and compare, and let's look at all of these here if we can. And we'll look at all the projects. So when I bring up the compare, the first thing it does, it tells me how many configurations I have in this model, so I can pick which configurations I want to compare with. And then any of the results features that I've selected previously, it tells me that it's available over here. So then I just click on the compare option. Okay, so it's doing all the post-processing, and then I go to active screen, and here are my three. I could compare the results for all three of these, and I can blow them up. We have surface parameters, and here is the goals. The surface parameters, something happened to that. I'll have to take a look to see what happened to that. These should all be filled in. The goal plots, you can see how you can compare your goals, the global goal min, average, and max for each of these. All right, let me close this out here. Okay. Now the next option that we have here is, this is kind of a helpful feature, and this was definitely a user enhancement request based on if you're doing an internal flow problem and you're trying to put a boundary condition on something, and it tells you that you can't apply a boundary condition because they can't tell between a fluid and solid region. I don't know if people have done that, they're familiar with that. And many times that error message means that there is no fluid volume. For people who are not familiar, in fluid mechanics or dynamics, it's a lot different than structure. Structures, you work on the solid part, so you always have the part there. But in fluid analysis, you're not working on an actual solid part unless you're doing heat transfer. You're mainly interested in everything else, the negative of the solid part. So flow simulation, and this is all done where people can't see, so it's done behind the scenes, actually creates SolidWorks parts of all the fluid region. And this is true for internal and external. But for internal, for it to know what's internal, it has to be completely airtight or watertight, so to speak. So if it's not, and sometimes when people are doing sweeps or they're doing extrudes, there might be like a really small hole, and sometimes they're really hard to find. Yes? Yeah, exactly. Yeah, because you're right, exactly. And unfortunately, you have to put another feature in there to block it out. But to help users find the holes, and there's not a lot of tricks you can do. You can do a cross-section and rotate it and try to see if you could see space on the other side, when you're rotating it. You could create a fluid region using the check geometry command for people, or a structure, click on the structure thing. But this new option is basically, it's supposed to help users find this area. So the leakage meaning the hole in your geometry somewhere that's preventing flow simulation from creating the internal region. So in the graphics area for this, you select your starting face, your ending face, and you tell it to find the connection. So it should be able, if it's completely internal, it should be able to find a connection, but it'll show you a line where there's a hole. And I'll show you, I have a model for that, so I could give it to you. Here's a little graphical explanation of it. In fact, here, what will happen is if you open a model that has this or do a rebuild or something, you'll get a new error message in 2013 that says fluid volume recognition has failed because the model currently is not watertight. An internal task must have sealed internal volume. You need to close openings and holes to make the internal volume sealed. You could close openings with created lids. You want to create a lids tool. Okay, so this, if you say yes, then you can go to the leakage tool because the leakage tool is actually in the create lids command, and we show that on the left over here. And in this particular model, you can see they selected the front face, the back face, and they selected the find button over here, and it drew a line over here saying that there was a small hole in this particular model, and it did that. Also in the lower right-hand corner, you'll see a little symbol saying non-watertight model. That's another clue that you have a hole somewhere, most likely in the model. And you can use the check geometry command just to verify that also. And in the help section here, there's a nice explanation for most users that you have in there. So let me go to back to our models here. And I think I brought something here. And Okay, there's that message. When I open it up, fluid volume recognition has failed because the model currently is not watertight. Let me just say no for now, just to show you this model. Let's see if I do a... section view over here. Okay, I made it kind of obvious so you could see the hole that's in the model over here. But if you go to the flow simulation drop-down menu, you can go to Tools, Create Lids. Please select a face over here. And what we're going to do is... oops, what did I do wrong here? All right, let me rotate this a little bit. Oh, I forgot to click on the other window. Okay, find connection, and you can see in this particular case, it drew a line, so it's pointing to the area. So if this was like a little sliver or something, you could see the red line, and you'll know where you have to fix the geometry in a way to create. So this was a user enhancement request to help identify these areas. All right. All right. But I'd like to move on now, and I thought that this would be interesting for some users. With computational fluid dynamics, since it's always nonlinear type analysis, and it's not as nice as some linear stuff where you got all these tricks and all these things you can do, because nonlinear tends not to be very forgiving when you're trying to solve fluid flow analysis. It becomes the diverging solution very quickly. But these were some recent support questions, general support questions about particular models that people were working on, and I sent it to flow developers, and we're actually able to help them out with a little bit of what they're doing. And this particular one is there a way to simulate a pressure wave caused by an explosion in the flow? And the known location, what was known to the user was the location of the explosion and the magnitude of the pressure wave in clean air set some distance away. So the developer's response was that the pressure waves caused by explosion they thought could be modeled, and they recommend using the transient option. So in your general settings command, you set the time-dependent box in the first one screen for the physical conditions. And you, under fluids, in the general settings command, you would set the laminar flow case and the high Mach number. I'm sorry, not, laminar flow and the high Mach number option. And you will get a warning message when it's solving, because initially it's high Mach number when it first starts to go off, but then eventually the velocity decreases significantly, but you can kind of ignore the low Mach number warning message that you get. And the source can be modeled by using a local initial condition, okay? So for people who are not familiar, you can actually create a part in SolidWorks, a feature, just extrude a part in any way, use the component control command to disable it, okay? So by disabling the solid part, you're telling flow simulation that it's a fluid region. And then you can apply initial conditions to that local fluid region. And that's what this last bullet part is saying. So you can use the local initial condition command on the disabled part that you created in SolidWorks. It's not suppressed in SolidWorks, it's still active in SolidWorks. Okay, and this model ran for 310 iterations. You can see the physical time, of course, is quite small. The CPU time was fairly quick, 487, actually very quick for CFD. And there were 406,000 cells. Because the pressure wave is rather intense, you have to have a lot of cells in there. You don't need a lot of solid or partial cells, just a lot of. And I actually created a little, I think I have to end this to show it, little video clip of it here. And so these are the three different time points, point 0001, 2, and 3. And you can see the pressure wave expanding as we're going out. So it was something new I learned too. I thought it was kind of a neat, but I thought also it might give you ideas on how to create local initial conditions with that little trick of using the initial condition command on that part that you disabled. All right. Oh yeah, and this is the mesh that was created, and this was that little local region where we created the component control command in this little area that I'm circling. And there was a local initial mesh to bump up the cell structure, so it's fine. Okay, another question. This one's actually up there. I put as a solution. How should I define underwater pressure for an external flow analysis structure on a seabed? We had a customer who was modeling these structures on the ocean floor, and he wanted to account for the pressure that they were seeing so many meters below the ocean surface. And it finds out that the flow developer says we don't necessarily do a lot of hydrostatic, because fluid dynamics is always assuming the flow is moving, though we actually did put a velocity on this also. But this is like a little trick to account for that extra pressure at the bottom of the seafloor. So to position your model assembly, place the origin of the assembly on the seabed, not the sea at sea level. So you would create an external analysis, okay? So, and then you would create a flat plate representing the seafloor, and you would want the origin, right at the seafloor that you have. And then in the general settings analysis, you activate the gravity command, okay, it's to turn on the rho GH term. And then select fluid, usually water, or you can input the seawater component. It's a little bit different, the density and things that change. And make sure that the density is at the desired temperature. So don't forget, as you get deeper, it gets colder and colder. Okay, and here we go. This is also in the general settings command, the initial and ambient conditions. Activate the pressure potential command. If you notice, there's a general settings, initial and ambient conditions. There's actually a initial pressure and temperature, so that it can create, it can do that rho GH term that you have in there. And what you're seeing is on the right-hand side, you can see how the pressure is less at the bottom, and it increases as you go towards the bottom of this particular object that you have. And on the left-hand side is a velocity plot. So we're actually representing some type of current that was going through this, so they can measure forces and things at the bottom of the sea floor. Okay. And what was interesting about this particular model is they actually had a grid, a bunch of these different structures. So we were actually able to use the periodicity command in the computational domain to just model one of these structures, because they were all equidistant from each other. So we can assume, because the downstream affected the upstream of the next one, next structure that was down there. Okay, and then one last one here was somebody was asking about solar radiation, and I thought this might be interesting for some reason, for some people who may be doing some solar radiation calculations, due to the sun. We actually have in the general settings command, and shown over here, where you can define solar radiation as location and time. There's also another option. There's a drop-down menu. You can pick direction intensity. So you can specify your own direction intensity of the source, or if you say location and time, there's a bunch of cities you can select all over the world. I picked Los Angeles for this particular example, but you can pick Los Angeles. You can actually specify the date and the time. So this is 12 noon. The Z direction would actually represent, you're actually specifying the zenith direction and the angle measured from the north. So it has an idea of where the sun is positioned at that particular longitude and latitude of the city that you actually selected. Okay. Flow simulation does not take into account considerations between winter and summertime, or maximum solar energy will always be at 12 o'clock. Okay, so that's the tables that they were using had these different requirements. So in this particular animation, what we have is we just have like a little pole here sticking out of the ground, and we're going to show the sun at 1 o'clock. So it starts out at 12, and then 1 hour later at 3, and then 4 hours later. And just to give you an idea, it ran for about 1,400 iterations. The physical time was about 14,000 seconds. CPU time was very quick because the cell counts were not that high, about 13,000 cell counts. And let me run this one. And what you'll see here are two things. I think, again, we're just looking at about 3 or 4. It shows you the time specified over here. And what's interesting is you can actually see the sun. Let me loop this a few times. You can see the shadow growing, and you can see the heat intensity going lower and lower as the sun is coming down. So we're like the sun when we're looking at this. So the source is coming from directly the way you're looking at this. So you can see the hot part is on this particular side. So you can see the sun right at 12 o'clock, right at the top, and then now the sun is sinking. It's sinking further, and now it's all the way, it's about 4 o'clock in the afternoon there. And again, if you look at the shadow, you can see the shadow growing as time progresses. Okay, and we're looking at leaving radiation flux, but you can also look at temperature. The flux is a little bit easier to see, the shadow and everything, but obviously you could do the same thing with temperature. Okay, so I thought that those were some interesting demonstrations that may help some people out there that does that type of analysis or requires it. What I'd like to do now is talk a little bit about a mesh, because a lot of our questions that we have on the support side do come with mesh. And a lot of models that I see that come in, I see people right away want to, go to shut off the automatic settings, and they want to go in and start changing things. And that's typically when people get in trouble. The automatic settings in flow simulation are very good. And I understand, especially people who've used other CFD software, even when I started using flow simulation, I always wanted to uncheck it and do it yourself. You're just used to it. Now, I say that with a lot of caveats, because there are cases where you have to turn it off, and there are cases that you have to go in, and I'll talk a little bit about it as our presentation continues. But the reason this is important is because the automatic settings, it tries to be very efficient the way it's set, so that it doesn't force you to run longer CPU times so you get quicker answers. And a lot of times, the meshes that you see with the automatic settings are very close to settings with the advanced settings that you may put in there. And as I go along, I'll try to be more specific of what I mean by that, okay? Now, with any program and any meshing tool that you have, as you know, with CFD, there's a preprocessor part of it, then there's a mesher, and then there's a solver. And all three of these have to work together to solve the problem. So meshing is just one of all these components. And at least on my point, you want to try to understand what the program is doing. So I'm first going to go through the steps of how the program thinks in a general way when it's creating these meshes, so that you have an understanding of that, because that's probably very important. And then I'll come back later with some recommendations from a user standpoint, what steps you can take. So this is not a user perspective. This is what the program does automatically behind the scenes that you don't see. And it does quite a lot. So first, the program creates this basic mesh with sizes that are governed by the computational domain, the control planes, and a number of base cells. So depending on, in your general settings command, the default is level 3, initial mesh command. When you open up the initial mesh, flow simulation initial mesh, 3, 4, 5, you see the numbers that increase there. So as you increase each of those numbers, the number of cells increases automatically in flow simulation in the XYZ direction, okay? So it always creates, for people who don't know this, brick type cells. So it's creating these nice squares, as you saw in some of the models, and you will see in some of the slides that are coming before. So not only when you increase that slider bar, you're also increasing the refinement, And you're also increasing the convergence criteria that you have within the model. So there's a lot going on there, and it looks very simple, but it's a very sophisticated wizard, that initial mesh wizard, okay? So it analyzes the triangulation of each base cell at interfaces between different substances. So as any fluid analysis, people who are familiar, the boundary layer is very, very important, very critical in any computational fluid dynamics problem. And that's what the partial cell does. I'm not, because this is short, I can't go into detail on the mesh, but there's 3 different types of meshes. There's the solid cell, the fluid cell, and the partial cell. And of course, the solid cell is 100% in the solid, the fluid cell is 100% in the fluid, and the partial cells, those are the key cells. Those are the that contains the boundary layer. And that's where flow simulation solver uses a special modified wall function to calculate that boundary layer, and which is critical in any CFD code. All right, so that's why these, that's why this bullet number 2 is important, because flow simulation does recognize interfaces, and it does recognize corners. So now when you get into curvature, it's a little bit different. You may have to start increasing because curvature gets a little bit more complicated, but we'll get into that in a little bit. So what the program is doing is on each of these cells, it actually triangulates. So it tries to find the maximum angle between normals, which compose the interface of these cells. So between a solid and a fluid, solid porous, solid solid. So the solid solid is important because of dissimilar materials, especially if you're doing heat transfer, you're worried about different conductivities. Okay, so depending on the maximum angle that you have on a particular model, the decision whether to split the cell or not is made in accordance with those terms, A through E. If you turn off the automatic settings box in the initial mesh command, all these options are under different tabs within there. So this is what people usually go in and they start changing it. But it's probably best to use the default settings, especially the first time you're running an analysis. We'll always recommend it, but I'll get into that a little bit later. So it worries about small solid features, narrow channel refinement, curvature refinement. So it does look at the curvature and it tries to further refine the cells around particular curvature. There's actually criteria that you can go in there and change. But again, the default settings are usually very good. Tolerance refinement, and if a cell belongs to a local initial mesh area, remember I showed you the example where we used the local initial mesh in the blast wave, the pressure wave that we were using. It actually recognizes that local initial mesh and does a nice smoothing process around it, because people who are involved in CFD understand that you can't have a large cell next to a small cell. It affects the numerical solver techniques that are going to try to reach convergence on that particular thing. So if the basic mesh cell is split, the resulting child cells, so the basic cell is the parent cell, that's the very first cell, and then when it starts refining it, they're called daughter cells or child cells, and described in 2 and 3 are split further. So the cell splitting will proceed until the interface resolution satisfies the small solid feature refinement criterion. And the specified levels of splitting denote the maximum admissible splitting that may show in a level basic mesh. Okay? So number 5, operations 2 and 4 are applied to the basic mesh cells and so on with 2 important rules. Okay? And these are really good to keep handy. Cell mating rule: 2 neighboring cells, cells having common face, can only be cells with levels that are similar or different by 1. And this rule has the highest priority as is necessary to simplify numerical algorithm in the solver. So this is where it grades the mesh. You won't see a big cell next to a small cell. And here's an example on the right-hand side. This is a 4-level cell appearing, resolving a triangular protrusion. So this is a basic cell here that you're seeing. Here's another basic cell, another basic cell. And again, remember, flow simulation looks at the split between the solid and fluid region. So it actually came in here and it refined these cells. And because of this protrusion that we have in the surface, it's actually refining it several more times until you get to the 4th level red cell. Okay, so this causes subsequent refinement, producing second cells, green and blue cells, and the white cells are the basic cells. So this is what the program is doing throughout your whole model. I mean, very quickly, it's looking for all the different protrusions, recognizing them, and trying to further. So when you're sitting there and you're watching it, you see those little refining, capturing, refining. That's what it's doing, is what you see it here. Okay. Now, there's one other important thing, is the optimized thin wall box. It's in the initial mesh command. So when you in the flow simulation drop-down menu under initial mesh, it's a little thing, little box. I think it should be like 5 times bigger than it really is because it's huge. When you have a thin wall with fluid on both sides, don't forget you have a boundary layer on both sides if there's fluid on both sides of that wall. So think of a heat sink. A heat sink has a lot of thin walls, and you have a boundary layer on each side of it. Before the optimized thin wall resolution option, the user would have to go in and have at least maybe 2 or 3 cells in a solid, and then you want small cells on both sides of the wall of the heat sink, as an example. And so you can imagine with a lot of fins, these things can grow quite large, and you get long CPU times, large RAM requirements, which, back 5 years ago and stuff, it was a big deal. It's getting less and less, but still the CPU time is there, and you can get answers much quicker. This optimized thin wall is very nice because it resolves without the mesh refinement inside the wall. You no longer have to go in and put 2 cells within each heat sink and make sure you have a nice grid pattern on both sides of the wall. Now, the optimized thin wall actually is 1 cell, and actually inside the program, it's using internally little cells to capture the gradients, thermal gradients within the, let's say if it's a heat sink wall, and in the boundary layer on both sides of the wall. So it's still being calculated, but it's in a much more efficient way than doing it ourselves, that we were doing it. All right, and here's just another slide on that. You contain more than 1 fluid or solid volume during a calculation has an individual set of parameters. So if the wall thickness is greater than that big cell, the cell size across the wall, or if the wall creates only 1 fluid volume in the cell, then the opposite sides of the wall will not lie within the same cell. So it'll go in and refine it. So these are resolved with 2 or more cells across. Okay? So that's what the program is doing internally. Okay? As users, what's the best thing that we can do? So at the beginning, create a mesh using the default setting 3. Always run it first. Any CFD person never runs a model just once. There's always a number of things. And there's several reasons for that, and I'll get into that in a little bit. But at this point, it's important to recognize the appropriate value of the minimum gap size. Okay, we have a special feature for the thin wall, the optimized thin wall that I mentioned in the previous slides. But there's nothing yet for the gap. So if the distance between the heat sink fins, we recommend that you put in that gap so you get extra refinement between the walls for added accuracy, depending on how much accuracy you need. All of this, if level 3 accuracy is good enough, then you don't have to worry about it. But normally people usually want to add that. And same thing with a valve. Let's say you're closing it, and it's a small opening that the flow has to squeeze through, a ball valve or something, then you would want to put that small opening as your minimum gap in the initial mesh command. Okay? All right, and then don't switch off the optimized thin wall section, which allows you to resolve the thin wall. So it's kind of repeating what I said before. Okay, number 2, closely analyze the obtained automatic mesh, paying attention to the total number of cells, resolution of the regions of interest and narrow channels. Okay, so CFD, like any analysis, you always have to have some idea of some result that you're looking at. So you want to validate it, and there's several ways, either with testing or analytical solution. And I'm going to show you one other way after this particular slides that we're going to have. But closely analyze it and compare it with something that you know. Now, if the automatic mesh does not give satisfactory results, changing the minimum gap size does not give the desired effect, proceed with steps 3, 4, and 5. Now, at the bottom, I say, please note that steps 3 and 4 can be skipped, and step 5 can be used right after step 2. Sometimes it's preferable, sometimes it's quicker. And a perfect example is that blast wave problem that I mentioned. We skipped steps 3 and 4 and went right to 5. We created a local initial mesh. So we created a feature in SolidWorks. So, an example is you have some hot component and you want to refine it. What you can do is create a solid feature in SolidWorks, right over it, go to the component control command, disable it, go to the local initial mesh, and bump up the refinement just in that local region, okay? And you won't have to use 3 or 4. But if for some reason you have other reasons, and if we have time later, I'll show you an example of that. We're going to start to create the custom mesh. You would go back to 3 and step 4. So this is, it depends on what you're doing. So you start to create the custom mesh by disabling the narrow channel refinement while the small solid feature refinement. So what they're saying is when you go to flow simulation initial mesh command, turn off the local or the automatic settings, and then you have all those tabs. And they're saying to go in there and actually set the small solid feature refinement and the curvature refinement to 0. This will produce only 0 level cells. So that's your basic cells, just the number of cells in the XYZ direction. Use control planes to optimize the basic mesh. Next, adjust the basic mesh step by step, increasing the small solid feature refinement and the curvature refinement. I'll show you an example of that in just a sec. Okay? Any questions on that? Or? Okay. All right. Some people may recognize this. This is one of our tutorial. It's in that tutorial.pdf file that I mentioned at the very beginning for resources. You'll actually find this in the intermediate guide, and there's a step-by-step for this. But it kind of goes over everything, these recommendations that we were talking about earlier. This is a vent. There's a fan at the top of it. This was used in lab. They were testing some dangerous chemicals. They wanted to keep the exhaust or the chemicals away from the lab technician. So here was the exhaust. So it's blowing air out or sucking air out through the vent. And this is an injector. In this particular example, this was a real customer model that we got, it's got to be about 8 or 9 years ago. So this is when we didn't have all these multi-core and 32-bit computer only, and you only have 2 gigabytes of RAM per process on a 32. So mesh and CPU time was very, very critical in this particular model because of the thin walls. We at this time, we didn't have the thin wall optimization option in initial mesh command also. So there's an injector that was injecting chlorine gas through here, and there were baffles here, so it vented the flow out through the exhaust over here. And the lab technician, this was open to air, so the lab technician was able to stand over here and not have to breathe this chlorine gas that was coming out here. And so just to give you an idea, okay, so this is 5.79 feet, just to give you an idea of distances here, from tip to tip. Now here, we're talking about 0.0044 feet. So we would call this a large aspect ratio model, meaning we have some very big computational domain that we have to account for, a large fluid domain external, but very, very small opening for the chlorine gas. Rather high velocity, so there's a lot of gradients, a lot of diffusion going on between the chlorine gas and the air. Okay, so that's what they're saying in the slide. Note that it's about 1,000 times smaller than the characteristic model size for this particular model. So when the user first tried to run this model using the default settings, just like we recommended, they got 1.1 million cells, which was way over back 8 years ago. You couldn't even run it on a 32-bit machine. So what we did with this model is we set the manual specification of minimum gap size to 0.067, which happens to be the gap size between the baffle walls, the smallest point between there. So we ignored the small gap of the ejector, which was 0.0044 feet. Okay, and what that did was it actually reduced the mesh count now to 200,000 just by that one little change. Okay, so we ignored the ejector. And I'm going to show you what we did after that. We didn't totally ignore it. We went back after doing that. Went to the narrow channel refinement, set the refinement to 1. This allows to reduce the total number of cells in the channels between the baffles and the wall, and resulting mesh, again, went down to 80,000 cells. Okay, so we're trying to make it more manageable. We'll worry about the ejector later. Let's try to get this as low as we possibly can and still get a good mesh for the rest of the model. Okay, so you can see there, we're showing you the model on the right-hand side, the mesh settings, and we still have about 2 or 3 cells between the baffle, the smallest distance between the baffle walls. And you can see how the refinement of the flow simulation, remember I told you how the flow simulation goes in, looks at the fluid regions, and tries to, the interface between the solid and fluid regions. So it's actually accounting for all these little spaces that are going in there. So it's actually going in there and refining all these corners, every place that you see here. Okay, so now that we got it down to a reasonable size, 80,000 cells, let's go look at the ejector. And we look at the hole, and you can see there's only 1 cell there. So there's no way you're going to be able to capture the gradients of that's going in there. So what are we going to use? To resolve this, we're going to use a local initial mesh, just like we did for that pressure wave. So we actually create a solid part, go to the component control command, disable it, and then use the local initial mesh command to better refine it. Okay, and you can see before and after pictures there, and you can see how there's much better refinement. We now have several cells across this ejector that has the chlorine gas over here. And what's also important here is what's coming up in the next slide. The cells are not, they're not symmetric across the hole. Now, sometimes you can ignore this, but in this particular case, because of the diffusion, the high velocity of chlorine, we wanted a much more accurate mesh. So this is where that step 4 with using control planes comes into the program. We want to make it a little bit more symmetric. By the way, in the local initial mesh command, I just wanted to point out, and this was actually a user enhancement request, this slider bar used to go up to 7, now it goes up to 9. They asked, they had a particular case where they wanted to go a couple of more levels up, further tweak the refinement. So the developers were actually able to go in there and add a couple of more points for that. Okay. So now control planes were set up. So control planes is you're just basically telling the program, okay, this is how I want so many cells in between 2 different places, and I want a certain grading. You can give it a certain percentage or a certain interval setting. And we're able to straighten out the mesh using these settings. And like I said, anyone's welcome to go to this model in a tutorial.pdf. I know I'm going kind of quickly, but there is a step-by-step in that you can go to with this. And you can see that there's a nice symmetric mesh around this particular ejector now, this 0.0044 feet. Okay? So here they're going over the steps for creating the local initial mesh. They're increasing the narrow channel refinement. Here is the local initial mesh. This is in the component control command that I mentioned earlier. Again, in people who don't recognize it or first time here, people who have been using flow simulation and component control was also redesigned a little bit. You can see it looks a little different than it normally does. It's now in the left-hand side by the flow simulation tree, manager tree that you see like before. All right, so here's the final mesh. So we went from 1.1 million to about 200,000 to about 80,000. And because we further refined the ejector, we're back up to about 100,000. So this is an order less comparing to the mesh generated using the default settings. You can see this on the left-hand side, this is the velocity plot of the ejector coming in here, and you can see the velocity heading towards the exhaust outlet. And this is actually a mass fraction plot of chlorine, actually volume fraction of chlorine. And again, it's being suctioned. There's actually a little bit of vortex flow that's going in there that was very interesting to the customer, and they were able to make some decisions on how they wanted to improve this hood design that they were looking at. Okay, now a couple of other quick tidbits. Another tricky thing sometimes, or not sometimes, usually, is rotating flow models. Rotating flow models can be tricky just because CFD cannot do moving geometry. And rotating flow model has spinning blades. So as a workaround, what they do is they use what's called a rotating frame of reference, where in the equations, for the actual Navier-Stokes equations, you can actually add the angular velocity as a body force term. So what you do is, just like the local initial mesh command, excuse me, you create a SolidWorks feature around the blades, a big solid, maybe cylinder block, same height. You want to go a little bit, I'll show you a couple of slides, a little bit past the blades to capture flow that's going around the blades. And you disable it in the component control command, just like I mentioned before, okay? And you have to select it as the rotating region. So all the cells within that rotating part, that feature that you disabled, will have that extra body force term of rotation, that angular velocity that you put in there. And then you can also select it in your local initial mesh command to further refine the mesh, because the velocities tend to be quite high in those regions. So that's what these slides are talking about. Choose the shape of the rotation so that the flow direction will be as much perpendicular to the rotating region as possible. So that's one of the limitations of the rotating region, is the flow has to be coming in perpendicular to the rotating region. So your inlet has to be up here somewhere. It has to be coming down. Now, people who are familiar with vertical wind turbines, we can't do that because the flow is actually coming in through the sides. So the rotating region, that's just one of the limitations for this workaround. There are some other applications. There's, like if you have a table fan sitting, some of the flow is coming in, not perpendicular, but that's okay. Most of the flow is coming in perpendicular. So you can kind of usually ignore that particular thing. Okay, so you want to use the simulated rotation part component of flow field, local rotating region. I talked, if you solve a problem with flow symmetry directly influenced, right, that's the other thing is the blades have to be axisymmetric about the axis of rotation. So you can't have anything that's not symmetric within the rotating region. And the rotating region, you can't like put holes or anything. It's got to be a solid region in there because it causes problems with numerical convergence. Okay, and this is kind of what I was talking about before. If we're looking at a cross section of the impeller, the image on the top is not recommended. You notice that the orange here is the solid component that we created that's going to represent the rotating region. You don't want to end it here because this could cause numerical convergence problems. What you want to do is make the part, it's no problem if this intersects, whoops, there's no problem if this intersects the solid because it's just going to create solid cells there and it won't introduce any fluid equations in the solid. So there's nothing wrong with that. Okay? And now here's an example. This is a fan that's actually used in industry that there's a heat sink mounted under the fan, and there's actually a copper core. That's that orange thing that you see, and then there's a very, very hot component that's dissipating a lot of heat right underneath it that they're trying to. So that technique that I've been telling you here about the rotating was actually used. You can see the solid feature right here. You can see it's slightly bigger than the impellers, but it's only the, this is with a transparency on, this is without it. This is a cross section. This CPU cooler, yes? Yeah, that's a good question. If you really need to know what the velocity vectors look around the impellers, you want to see how it is, then it's important. But for most electronic cooling problems, you don't need to do, you can use a fan option because you're mostly interested in the airflow that's coming out and the pressure drop that's creating. And as long as you have a pressure drop flow rate curve, which most electronics, people are doing electronics, is that what you're referring to, electronics cooling? Yeah, that's what I anticipated. And so if you're doing electronics, and also these rotating flow problems, the CPU time, the number of iterations go up. It's a much more problem to solve. So it's easier with a fan. It's faster.
But you would say this is probably more accurate than using?
No, I mean a fan curve could be very accurate. This is only for people who have water pumps, compressors, use this type of a fan that you stick on your desk. I've seen some people use that, the rotating frame of option. So so I've seen people who, they were making this big industrial fan to dry floors of a distribution center or something. It was wet and they want to bring in fans. So they actually were designing these fans and they wanted to change the pitch or something of the blades. So if that's your design intent, is to do an analysis on the blade itself, then you would probably use the rotating, you wouldn't use the fan option, but the rotating, because as you change that, then the pressure drop flow rate curve would change and they wouldn't help you out. So you wouldn't use the fan option for that. But if you know, if you know the fan curve, then you can do that industrial drying application with the fan option if you don't care about how the propeller is designed, if that's not your intent. Does that help? Or? Okay. And this is, again, this is in the tutorial.pdf file, and you can go through it step by step, and they give some detailed, as you could see, they give you some more hints about where to worry about gaps and things like that within the model. Here, this was actually set at result resolution 5, minimum gap size of 0.001 meters, and that's because the gap between the fins, if you remember, there was some circular fins underneath the fan. That's where the gap thickness was chosen. So the fan and heat sink better, so the ratios for the intervals between them to make it denser. So there was some control planes added. That's why you see this particular mesh, and mainly it was because of the heat sink that was in there. Okay, but what they did was they first ran it at result resolution 5, and then came back and added some control planes to affect the mesh. And there's an image of it, and you can see. And this is typical of a rotating region. Here is the angular velocity, and you can see how there is some discontinuity because you have an angular velocity body force term in the equations, and in the next cell right outside the rotating region you don't. So that's inherent, that's a limitation in using it. But it's better than not be able to do anything at all. But it doesn't affect the overall solution. You still get good results. We've had people say that they were able to get good temperatures and stuff on their CPUs using this particular option. Okay, these are two different section views that we're looking at in this particular model. All right, and then just to drive home a little bit about the meshing, just to give you an idea, these were some validations, and in fact they're in the technical reference guide that they have. And basically what we're showing here is, what I want to get out is you first run it at level 3. And if you're happy and satisfied with the results 3, there's no reason to use control planes and local initial meshes. This is only if you suspect that there's a problem or you compared it to something else and something doesn't look right enough and you need more accuracy. In this particular case, to get more accuracy, we set the result resolution to 5, okay? And we set the minimum wall thickness to 3 millimeters. Now the reason for the 3 millimeter wall thickness was because of the sharp edges, and what they did was unselected the optimized thin wall section. So this was to get a better refinement around this. If you notice, this particular valve has a very, very sharp edge to it, and they wanted to be able to capture. So you can see the program automatically looking at the solid fluid interface and coming in here and refining all of this. So with not a lot of meshing problems, in a lot of other flow simulation, you have to set up the mesh yourself in some cases, and this would take a lot of time. But it was just basically moving slider bars and setting minimum wall thicknesses, and you can see on the left-hand curve, we were able to get very accurate results based on some test results that the customer gave us on this particular model. All right, and now this was a simple laminar flow between two parallel plates. Again, result resolution 5 was used. We did both Newtonian and non-Newtonian fluids in here. So Newtonian is when the stress-strain curve is linear. Most fluids like water and air are Newtonian. Non-Newtonian is more like blood or plastics. You start getting into a nonlinear stress-strain, and viscosity starts to do some strange things with it. But in all cases, a result resolution 5 was able to get good results. And you can see the mesh refinement in this region. This is a velocity plot. You have the walls. And you didn't really need a very graded mesh towards the walls. You could see that the mesh is not infinitely small to get the right result. We were able to use fairly large cells in this particular and still get match results very well within this. Okay, now tips for refinement of the computation during the calculation. Something that I haven't talked about yet is, you notice I always stopped at 5, the result resolution 3, 4, and 5. There are actually other levels beyond that, 6, 7, and 8. And what happens is there's an adaptive mesh refinement that automatically gets triggered when it's. Now, most of the problems, industrial applications, you don't require it. I'll show you some where people usually turn it on. But it just adds more cells, and it could get quite large, and also increases your CPU time. So that's why it's usually not needed, but there are some cases. So in Flow Simulation 2012 SP2, they actually enhanced the solution adaptive refinement and kind of reworked the inputs. They actually took out a bunch of inputs. There's very few refinement techniques that are required. You can specify an approximate maximum number of cells. So just by having that option, you can tell that sometimes this can grow very large if you have to input what the maximum cell count is, just to keep it within what you're working with. Okay? So here is an example similar to those weather plots that I showed you earlier with the vortex shedding on a cylinder plate. And the automatic refinement was set for this particular model. Okay, so there were different cylinder diameters in water. And you can see that we used the result resolution of 6. So remember I told you 6, 7, and 8 are when the automatic. Now as you go up, there's more refinement done. And what it's looking at are gradients in the solution where temperature, density, velocity, pressure, where there's high gradients, it's going to, it runs the solution for 30, 40, 50% of the way towards convergence, and then it automatically stops it, and it searches all the cells, and wherever it sees a large gradient across the cell, then it goes back and it further refines that area, and then it restarts. It's all done hands off, the user is not involved in it. And it remeshes it, and then it starts up again where it last stopped from, and then it continues the solution. And whether you have 6, 7, or 8, it'll do it more times. So, 7, that might happen 2, 3, 4, 5 times, depending on the criteria, the internal criteria, whether it's required more. And so you can see in this particular, the adaptive refinement was basically in this general area, and you can see it kind of tapering off down here because the gradients are becoming more centralized within this particular model. Okay, here is another, this is actually a supersonic flow problem, 2D converging, and this is actually, from literature, we know exactly where the shock waves occur on off of each of these, and you can see in the model that they are captured, and you can also kind of look at the solution adaptive mesh that was turned on at result resolution 6, and you can almost see where the shock waves are in relationship to the mesh, and you can definitely see the gradients, the high gradients. This is Mach number that we're seeing. This was Mach 3, actually, the inlet. Okay, and this is another supersonic flow over a segmented conic body. This is interesting. They do it, if you look at the validation example in a technical reference, and you can, the model is also up there. When you install flow simulation under the validation examples, you'll actually can run this model and see it, and you can. It's saved. Each configuration is at a different angle of attack, so it's kind of cool that you can see how each one looks different, and you can see how it compares to known results, and we've got good correlation with known results. Here's a convection and radiation problem, again at result resolution 6. And again, we were able to match with theory. So just by using the slider bar, a lot of times you can get what you need. You don't always have to turn off the automatic settings box, which, by the way, is right here in the lower left, automatic settings. So you don't really need to turn that off. And then here's the optimized thin wall thickness box that I mentioned earlier. Okay. And here is an example. This is an electronic cooling, a pin fin heat sink. What we have is an electronic component with some pin fins. So instead of these heatsink fins that you're used to, these long, narrow channels, these are like little pins sticking up, and there's a lot of air in between it. So you've got air, solid, air, solid, air, solid. So the refinement in here, we actually were able to run it. This was a 9x9 pin array section at resolution 3. We did specify a minimum gap size, and this was actually the thickness between each of those pin fins that we had in there. And here's a little close-up of the substrate. It was mounted on a sidewall like this, so gravity is in this direction here. Here's a little cross-section of the pin fin. And here's a smoke test that was done to measure how the natural convection, so there was no fans or nothing, no forced air cooling. And you could see it, the hot air rises, and then it cools, it comes back down, and it creates this really nice vorticity pattern here, almost like the numeral 8. And you can see flow simulation. These are flow trajectory plots that were able to capture it. Okay. And here is another one with the, this is isothermal cavitation in a throttle nozzle. So we're actually injecting, this might have been diesel fuel. I can't remember what, I think they may even say, do they say in this? No, I think it's diesel fuel. Yeah, 3D diesel fuel into a very narrow channel. And you can see in this particular case, we actually had to add a local initial mesh in that narrow channel, especially near the inlet and at the outlet. So where you have compression here and expansion. Now cavitation, if people are familiar with, we're actually taking a liquid and it's turning to a vapor because the velocities are so high that it's actually boiling at that point. And so you have two-phase flow in certain regions. And flow simulation cannot do two-phase flow. It does a single flow, but we have a cavitation option. It's under the fluid, general settings, fluids. You can click on it, but it needs a very large mesh count, okay? Normally, especially for this high velocity, which cavitation usually requires very high velocity. And as we increase the flow rate, these plots at the bottom, you can see the cavitation region growing and getting longer. And you can see the comparison to actually test data, and it expanded very well with that. Okay? So now, what I'd like to do is take everything that we talked about mesh and talk a little bit about convergence. I've kind of implied it, talked about it a little bit, but just to give you an idea now, as you know, we talked about computational fluid dynamics. There's no closed form solution, so they solve it by solving the right hand part of the equation and the left hand, and they do a time marching technique to try to get it equal. They never exactly equal, so that's why we have this issue with convergence and trying to decide when to stop a solution. There are some CFD programs don't have an automatic stop. You as a user decide when to stop it. Because the developers are too scared to do that in some other models. But in flow simulation, there is a automatic stopping. It's usually very good. There are times where it doesn't need to run as long and you can stop it early, or there's times where you may have to extend it. And that doesn't happen very often, the extending part of it, but in some cases it does. Natural convection is one of them because you have temperature. Initially, everything's at room temperature, and then you got a heat source, but no flow. So the component is getting really hot, and then it heats up the air. The air gets hot, and it creates a convective current. So then the component temperature comes down again. This is during convergence. So you know, if you have too coarse of a mesh, it may stop too early. So you may want to run it. But if you have a refined enough mesh, you normally don't have to worry about this. Okay, in the flow simulation drop-down menu, there's something called the calculation control options command. Okay, the default, the very first one, and this should be in big red letters if one is satisfied. Okay, so it means if one of these conditions below is satisfied, it's going to stop the solution and it's going to say it's finished. Okay, so this is where this is a gray area convergence. This is where you have to check, make sure your results look normal. You have to do a sanity check, either with analytical solutions, any validations that you have on there, anything else that you have. So you can increase the number of maximum iterations if you want to run it longer. You can increase the calculation time. Travels, we don't have enough time to get into it. Most of the time I don't bother with it. It has to do with numerical number for how long it takes a perturbation, numerical perturbation to go from the inlet out. But I see it's too much already. I don't want to go that far. So most of the time you'll do with maximum iteration, mathematical physical time, CPU time. Stop the solution, take a look at it, see if you're happy with the results, continue the solution. Now, what's nice about it, when the solver monitor is up and running and you're watching the solution converge, you can, in the file edit, you can drop down the calculation control options and change it on the fly. You don't have to stop it and then change it. You can actually, so it'll take effect the very next iteration. Okay, so when you have that selected, when you go into the calculation control command, when the solver monitor is winning, it'll actually pause the solution for a second, wait for you to make your decision, and then it'll continue depending on. So this, if one is satisfied, also has to go with goals. Now we always recommend to set goals. The goals are, and I've showed you a number of them through the presentation that we had today, could be pressure, temperature, velocity. You create your own equation goal on pressure drop, temperature drop, efficiency. I see people create all kinds of equations. And what you can do is, it's also affected by this calculation. If you say one is satisfied, if one of the goals converge, there's a caveat to that, I'll come back to that later. If one of the goals converge, the solution may stop. But flow simulation has a backup. It doesn't want to stop a solution too early. So it has to run a certain number of iterations. And I can't tell you that number because it's unique to different types of problems, depending on what you're doing, natural convection, radiation, rotating frame. So it's going to run a set number of iterations before it allows if one is satisfied to take into effect. Okay, so there are backups. Also, flow simulation has built into it conservation of mass, momentum, energy. So it has to satisfy those things too before it's converged. Okay, if you're a little worried about if one is satisfied, you can change that to if all are satisfied. And there's a little drop-down menu that go for that. Okay, we just got a couple of, so in flow, it has an automatic convergence check feature that allows the solver, when criteria is met, the solver can stop manually if necessary. The only general is called grid convergence. And this is that other method that I mentioned earlier. If you don't have something to validate your results to, if you don't have an analytical solution, test results, anything, this is one method CFD users use. Just about most CFD analysts will go to this. Create a first mesh relatively coarse and solve it. Clone the project. Create a second mesh, which is finer than the first one. Compare the results. You can use the new compare tool in 2013. Only create a third mesh, more refined to step 2, if the results are significantly different than steps 1 and 2. Continue refining the mesh until the last 2 runs results, you have the last 2 are relatively small. So this is called a grid convergence, a mesh convergence. There's a lot of different names for it. Independent solution with the mesh. There's a lot of people call it different things, but this is a good technique to know that with the boundary conditions and the mesh that you have, it is fairly okay. And then these are just more things about the goals, and I've talked at length about goals. So I think people are pretty familiar with. I mentioned the global surface volume equation goal that we had before, and this is a typical solver monitor plot. You could see how the temperature in this particular was quite high. It started at initial temperature high, and as it was converging, it converged to a nice solution. Now, when flow simulation is checking for convergence, do you see this little white bar? You can kind of just barely see it across the bottom over here. It's checking the last and the first and last iterations here. So this is like iteration 41 and maybe iteration 22. And that's what it's comparing what's going on here, because you don't want to do the last 2 iterations, because you can be on a slope downward or upward. So it's looking, and this is CFD analysts, well, how they do it in other codes. They'll look at 50, 100 iterations. In flow simulation, you can change the analysis interval on that if you want in the calculation control option. No, actually, in the calculation control options command. But the default is usually pretty good. And it changes depending on the problem that you have. So it's smart enough to recognize that. Okay, and remember that bar that I was telling you that it looks at the first or last? That's what the value is the last iteration. The average is the average value, a parameter across that bar. The min and max is the min and max across that bar. And it tells you each goal, what the convergence, whether it was used for convergence, the delta, and the criteria for convergence. Okay, so that bar was 42 iterations long. And here's another where it started low and then it went high. Okay, we're right at 6 o'clock, and I know people are waiting to go somewhere. So I'll let you. Any questions before I go, or let you go? Yes.
I did CFD before. I'm wondering if the domain size will affect the result.
If the computational domain size?
Yeah.
Yes. Oh, yeah. For external analysis, it can. So I know that's a common question. Thank you, everyone. Thank you very much for coming. What happens is, again, there are really general recommendations for that. But really, you have to do trial and error type comparisons. If you're doing external flow analysis, let's say around a car body or a wing or something, you want what happens is, in just like other programs, they have what's called a pressure-free boundary condition at the front. So if you have gradients that cross that computational domain with the pressure field that's assigned to that, it could potentially affect your results. It's kind of like a wind tunnel. Wind tunnel people have the same problem. You know, they stick the wings. That's why they can't. It's really hard to do full-scale models, because you can't get a wind tunnel like for a 787 or some of these other things. So when you try to make it smaller, but there's papers written on wall effects to the actual results that they're having. Same thing in computational domain, but what's nice about computational domain, it's a lot cheaper. Just, you can just artificially make it bigger, where in testing, you can't make a bigger wind tunnel. It's too costly. But normally downstream, you want to make it 10 diameters. Above and below, it's 3 to 5 diameters, and maybe a couple of diameters in front of the vehicle. It depends on the velocity and how much drag is on the vehicle and what the recirculation is behind it. But you've seen some of those. There are validation examples you saw of the cylinder with the vortex. And there's a couple of other external flow problems in the validation, and you can kind of maybe gauge. But it is a trial and error. You got to run it once and see if you got good results, and then compare it. Yes?
That's a case where just make a big computational domain, make it very coarse, and just see what it tells you.
Yes.
There's a lot of stuff going on behind it, and you need more mesh behind that to resolve what's going on behind it. If you're studying the weight, if you're just studying the object, surface mesh will tell you what you need to know about the object if you want to know the forces. And like Bill said, you'll still have wall effects. You'll see that, and typically wind tunnel, you want the object to be 7 to 10% of the throat area, and you minimize that in the wall effects. And if you do that and try to get a lot of wind tunnel stuff, you'll see it on the edges, but it doesn't affect.
So yeah, the wind tunnel people, the problem they have is the velocity goes to 0 at the walls. Where in our case, we don't go to 0. It's a pressure condition.
You can move ground 400 miles an hour in the air, or they can't do that.
Right.
But let the software tell you. Just do it about, throw it out there and look at it. Say, oh yeah, I see. It says there's something going on here. Or a lot of times that's where the adaptive comes. Just let you turn it on course, turn on the adaptive, and it'll tell you where the areas of interest are.
All right, thank you. Thanks. Any other questions? Yes.
Why would that option be on by default?
It is out by default. Yes. No, we don't recommend unselecting that. It's usually 199% of the time you want that checked. So yeah, by default it is checked on there. No problem. Yes?
I do a lot of simulations with particle tracking.
Yes.
So I'll introduce particles as a source and then track them through the model, and I'll select the surface and measure the mass accumulation rate.
Right.
Particles touching that surface.
Okay.
So I'm interested in the goal optimization, because that's what I'm doing, is I'm trying to make particles not land on a certain surface. So I wonder if there's a way, if that would be an option as an output, for it to run the particle study as part of the solution, and use that to optimize the flow.
Wow. I'll bring that up with the developers. We can't do it because the particle study is done. It's Lagrangian formula that they use in the post-processor. So it's something that's done afterwards. So it's not part of it, but that's a really good enhancement request or something to add to it. I like that. You're the first person that I've heard recommend that or say that they're doing something like that. That's very good. So yeah, I'm sorry. Yeah, it would be. I think a little bit the what if might help you, because you could do a lot of different things. Goal optimization, it depends on the problem. You can maybe use it if you know another parameter affects the particles. If velocity, a certain velocity, right, depending on, like, I don't know the specifics, but there might be some relationship between excuse me, the inlet velocity, my throat's getting dry, it's the end of the day, and how many particles. So, you maybe do the what if study with different velocities, also track how many particles for each one of them accumulate, and then if you see a different correlation, then maybe you can do a parametric study on the velocity. That's one example that I can think of. Okay, thank you.